Hello everyone, welcome back to my YouTube channel. So in this video, let's start with transformers and generators. That is nothing but T and G, module 1 for electrical and electronics engineering department. The module 1 is single phase transformer. So in this module 1, I'm going to explain you something about practical transformer on load. Okay. So before briefing about this practical transformer on load, we should know about practical transformer on no load. Then you'll understand this concept. Okay. So now, without wasting time, so I will explain something about practical transformer on no load. Okay. So let me take one slide. Okay. So under practical transformer on no load, you should know there is a transformer. It is having a primary winding and secondary winding. I hope basic principle of transformer everybody knows. But the word itself says practical transformer, practical transformer on no load. Means there is no load in a secondary side. So the transformer which is having primary winding and secondary winding, but the secondary winding it is open. There is no load. So in the primary winding, we'll be giving some supply voltage. Say it as a V1 you are giving. Current I1 is flowing. I can say that as no load current I0 which is flowing through the primary winding which is having number of turns N1, number of turns N1. Whenever the supply which is given to the primary winding of the transformer, the current starts to flow through the primary winding. So due to this flow of current, the flux which is produced with the help of thumb rule, and it will give you the direction of flux. Hence the flux which is produced in a transformer, and it starts to producing and started to linking with the secondary winding. So due to the linkage of flux in a secondary winding, there is in the current that will be induced in secondary side also. Due to this secondary current, EMF that will be induced in a secondary side. But as there is no load, hence current flows to the load is zero. With respect of that, in a primary side also it produces EMF E1, that is induced EMF. You can call that as a self-induced EMF. That will be always same as V1. I can write here V1, which is almost equal to E1. Okay. At the same time, E2 that will be same as terminal voltage or else load voltage. So here there is no load, no load current is flowing, that is I2 is zero, but there is a EMF E2. Okay. So under no load condition, EMF E2, which will be always same as supply voltage as well as the flux that will be produced, you can refer it as a phi. But under no load condition, what happened? There is a no load current I0. So this I0 or else no load current, you can also call it as I1. This I0 is having two components, two main components it is having. The first component is IC. You can call this as core loss component. Core loss component. Since secondary side which is open, hence there is no current in a secondary side, hence copper loss in a secondary side is negligible. Cu is negligible, but iron loss which is more. Iron loss is greater than copper loss, but copper loss which is negligible. And in the same case for the primary side also, a small amount of copper loss which will be produces, small amount of primary copper loss will produces, but iron loss will be always greater than copper loss in a primary side also. Hence, if there is no load, the transformer which will be producing iron loss, there will be small amount of copper loss, but that will be negligible. So that it this no load current which is having two main components. The first component which is core loss component, which is responsible. What is the function of this core loss component? Which is responsible to produce, which is responsible to produce iron loss or else core loss. Core which is made up of iron, so that you can also call this as iron loss or core loss. Iron loss, and also this core loss which is always in phase with V1, that is input voltage. Okay, and one more component which is there, that we can call it as magnetizing component, IM, magnetizing component. The word itself says magnetizing, which is responsible to produce flux. The function of this is to which is will be responsible to produce alternating flux phi. Okay, so which means that IM which is always in phase with the flux phi. Okay, so you should remember few things. If the practical transformer which is having no load, means there is no current which will be flowing in a secondary side, hence copper loss which is negligible, but there will be iron loss. At the same time, primary winding side which will be having a small amount of copper loss, hence if there is no load means transformer which will be producing iron loss or core loss. So that this no load current which is having two components, one is core loss component which is responsible to produce core loss or else iron loss, and one more piece magnetizing component which is responsible to produce alternating flux phi. So if you can refer the phasor diagram, you know that the flux is a reference. To produce this alternating flux, magnetizing component which is required, IM, and the E1, whatever you can call it, the E1, that is self-induced EMF and mutually induced EMF, E1 and E2, which are in phase with each other, and this E1 and E2 lagging the flux at an angle of 90 degree. And the V or else IC, the core loss component, which is always parallel to flux, and the V1 which is always in phase with the IC, or else IC is always in phase with the V1, whereas V1 equals to E1, so that I am writing the antiphase of E1. So if you're adding this IC and IM, you will get no load current I0, and the angle between I0 and V1 is phi naught. Okay, this is how you'll be writing the phasor diagram for no load. So how can you write this IC and IM? So whereas this IC is IC with respect to I0, you'll be having two velocity components now. So you can write IC is nothing but I0 cos phi naught, and IM is nothing but I0 sin phi naught. So which is a basic, if you can consider a triangle of this IC, and here you can see this is IM and this is your I0. This is the angle phi naught. If you are defining cos phi naught, you can get IC, that is I0 cos phi naught. If you are defining sin phi naught, you'll get IM, that is I0 sin phi naught. So this is about practical transformer on no load. Similarly, you can see a practical transformer on load. Okay, so you can also call this as MMF balancing, practical transformer on load or else MMF balancing. So for this practical transformer on load, you can see two diagrams here, the left side and the right side. So before going to see about the second diagram, first you can see the first diagram. So you can see a very simple explanation for practical transformer on load. So you are giving supply voltage V1 to the primary winding of the transformer. The current I1 starts to flow, and it produces the alternating flux phi 1 or else main flux phi, and this is linking with the secondary winding of the transformer. Current is induces, hence EMF E2 is also induces. Due to the induction of this current I2, the secondary winding of the transformer also, which produces its own flux, that is phi 2, and the direction of this phi 2 is opposing the direction of main flux, due to which what happened, the self-induced EMF and the difference between self-induced EMF and supply voltage, that is V1 and E1 V1 minus E1 will be going to increases. Means if there is an additional flux which is producing due to the induction of current in a secondary winding, that is phi 2, that phi 2 is opposing the main flux. Due to that, what happened, the main flux is going to reduces. If the main flux is going to reduce, means the difference between supply voltage and self-induced EMF will be going to increases. Means V1 is going to decrease, hence the difference is going to increase. So it is disturbing to the main flux of practical transformer. So to maintain the balance, to maintain or else to neutralize the alternating flux phi, what we are going to do, will be producing additional current, or else due to this difference, due to this, if this difference increases, means there will be a need of additional current. Hence the additional current that will be flowing through the primary winding of the transformer in the same direction of main flux phi. You can see this is phi 2 dash now. So which means that the additional current, the flux which is produced due to the additional current of primary winding of the transformer, that will be opposes the flux that will be produced due to secondary winding of the transformer. Means that phi 2 dash is neutralizing phi 1. So sorry, phi 2. Phi 2 dash is neutralizing phi 2 to neutralize or else to maintain the main flux. To not to disturb the main flux, will be giving additional current to the primary winding of the transformer. So which means that in the secondary side, we will be having the MMF of N2 with respect to I2. So here this MMF, which will be same as the primary side of the MMF, only if there is an additional current, that is I2 dash. Hence the transformer which will be, or else the MMF that will be balanced if N2 I2 which is same as N1 into I2 dash. I2 dash is additional primary current that will be producing through the transformer to maintain or else to neutralize the main flux by avoiding the additional flux that will be produced due to secondary winding. Means that it is reducing the phi 2. Okay. So how will write now this additional current I2 dash, which is given by N2 divided by N1, N2 divided by N1 into I2. So you know that N2 by N1 is nothing but transformation ratio, so that I2 dash equals K into I2. This is what you can call this as MMF balancing. Okay. So in general, if you want to know in a Kannada means, I will tell you in a Kannada also. ಸೊ ಇವಾಗ ಪ್ರಾಕ್ಟಿಕಲ್ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಆನ್ ಲೋಡ್ ಅಲ್ಲಿ ಏನ್ ಮಾಡ್ತೀರಾ ಅಂದ್ರೆ, ಲೋಡ್ ನ ಸೆಕೆಂಡರಿ ಸೈಡ್ ಅಲ್ಲಿ ಕನೆಕ್ಟ್ ಮಾಡ್ತೀರಾ, ಪ್ರೈಮರಿ ಸೈಡ್ ನಿಂದ ಸಪ್ಲೈ ಕೊಡ್ತೀರಾ, ಅವಾಗ ಪ್ರೈಮರಿ ಕರೆಂಟ್ ಏನಾಗುತ್ತೆ ಪ್ರೈಮರಿ ವೈಂಡಿಂಗ್ ಅಲ್ಲಿ ಫ್ಲೋ ಆಗ್ಬಿಟ್ಟು ಮೇನ್ ಫ್ಲಕ್ಸ್ ನ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡುತ್ತೆ. ಸೊ ಆ ಮೇನ್ ಫ್ಲಕ್ಸ್ ಸೆಕೆಂಡರಿ ವೈಂಡಿಂಗ್ ಲಿಂಕ್ ಆಗ್ಬಿಟ್ಟು ಕರೆಂಟ್ ಇಂಡ್ಯೂಸ್ ಆಗುತ್ತೆ ಸೆಕೆಂಡರಿ ವೈಂಡಿಂಗ್ ಅಲ್ಲಿ. ಸೊ ಆ ಕರೆಂಟ್ ಇಂದ ಮತ್ತೊಂದು ಫ್ಲಕ್ಸ್ ಪ್ರೊಡ್ಯೂಸ್ ಆಗುತ್ತೆ ಸೆಕೆಂಡರಿ ವೈಂಡಿಂಗ್ ಅಲ್ಲಿ, ದಟ್ ಇಸ್ ಫೈ 2. ಸೊ ಇವಾಗ ಸೆಕೆಂಡರಿ ವೈಂಡಿಂಗ್ ಅಲ್ಲಿ ಏನ್ ಫ್ಲಕ್ಸ್ ಪ್ರೊಡ್ಯೂಸ್ ಆಗುತ್ತಲ್ವಾ, ಆ ಫ್ಲಕ್ಸ್ ಮೇನ್ ಫ್ಲಕ್ಸ್ ನ ಅಪೋಸ್ ಮಾಡುತ್ತೆ. ಅಂದ್ರೆ ಅಡಿಷನಲ್ ಫ್ಲಕ್ಸ್ ಇಂದ ಏನಾಗುತ್ತೆ ಮೇನ್ ಫ್ಲಕ್ಸ್ ಗೆ ಡಿಸ್ಟರ್ಬ್ ಆಗುತ್ತೆ, ಅವಾಗ ಮೇನ್ ಫ್ಲಕ್ಸ್ ರೆಡ್ಯೂಸ್ ಆಗುತ್ತೆ. ಮೇನ್ ಫ್ಲಕ್ಸ್ ರೆಡ್ಯೂಸ್ ಆದ್ರೆ ಏನಾಗುತ್ತೆ, ಸಪ್ಲೈ ವೋಲ್ಟೇಜ್ ಕೂಡ ರೆಡ್ಯೂಸ್ ಆಗುತ್ತೆ. ಸೊ ಇವಾಗ ಅದನ್ನ ಮೇಂಟೈನ್ ಮಾಡಕ್ಕೆ ಏನ್ ಮಾಡ್ತೀರಾ ಅಂದ್ರೆ ಡಿಫ್ರೆನ್ಸ್ ನ ಇನ್ಕ್ರೀಸ್ ಮಾಡ್ತೀರಾ. ಯಾವ ಡಿಫ್ರೆನ್ಸ್ ನ, ಸಪ್ಲೈ ವೋಲ್ಟೇಜ್ ಮತ್ತೆ ಸೆಲ್ಫ್ ಇಂಡ್ಯೂಸ್ಡ್ ಡಿಫರೆನ್ಸ್ ನ ದಟ್ ಇಸ್ V1 ಮೈನಸ್ E1 ನ ಇನ್ಕ್ರೀಸ್ ಮಾಡಬೇಕು. ಸೊ ಅದನ್ನ ಇನ್ಕ್ರೀಸ್ ಮಾಡಕ್ಕೆ ಏನ್ ಮಾಡಬೇಕು, ಅಡಿಷನಲ್ ಕರೆಂಟ್ ನ ಕೊಡ್ಬೇಕು ಮತ್ತೆ. ಸೊ ಅದಕ್ಕೆ ನೀವೇನ್ ಮಾಡ್ತೀರಾ, ಪ್ರೈಮರಿ ವೈಂಡಿಂಗ್ ಗೆ ಅಡಿಷನಲ್ ಕರೆಂಟ್ ಕೊಡ್ತೀರಾ, ಅದು I2 ಡ್ಯಾಶ್. ಸೊ ಇವಾಗ ಅಡಿಷನಲ್ ಕರೆಂಟ್ ನ ನೀವು ಪ್ರೈಮರಿ ವೈಂಡಿಂಗ್ ಕೊಟ್ಟಾಗ ಈಗ ಆಲ್ರೆಡಿ ಎರಡು ಫ್ಲಕ್ಸ್ ಇದೆ, ಒಂದು ಮೇನ್ ಫ್ಲಕ್ಸ್, ಇನ್ನೊಂದು Φ2, ಅದು ಸೆಕೆಂಡರಿ ವೈಂಡಿಂಗ್ ಫ್ಲಕ್ಸ್. ಅವೆರಡು ಅಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಇದೆ. ಅಡಿಷನಲ್ ಕರೆಂಟ್ ಕೊಟ್ಟಾಗ ಏನಾಗುತ್ತೆ, ಮತ್ತೊಂದು ಫ್ಲಕ್ಸ್ ಪ್ರೊಡ್ಯೂಸ್ ಆಗುತ್ತೆ, ಅದು Φ2 ಡ್ಯಾಶ್. ಅದ್ರದ್ದು ಡೈರೆಕ್ಷನ್ ಏನಿರುತ್ತೆ, ಸೇಮ್ ಆಸ್ ಮೇನ್ ಫ್ಲಕ್ಸ್, ಬಟ್ ಇದು ಏನ್ ಮಾಡುತ್ತೆ, ಸೆಕೆಂಡರಿ ವೈಂಡಿಂಗ್ ಅಲ್ಲಿ ಪ್ರೊಡ್ಯೂಸ್ ಆಗಿರೋ ಫ್ಲಕ್ಸ್ ನ ಅಪೋಸ್ ಮಾಡುತ್ತೆ. ಅಂದ್ರೆ ಅವೆರಡು ಅಪೋಸ್ ಆಗೋದ್ರಿಂದ ಅವೆರಡು ಕ್ಯಾನ್ಸಲ್ ಆಗ್ಬಿಟ್ಟು ಮೇನ್ ಫ್ಲಕ್ಸ್ ನ್ಯೂಟ್ರಲೈಸ್ ಆಗುತ್ತೆ. ಸೊ ಅವಾಗ ಸೆಕೆಂಡರಿ ಸೈಡ್ ಅಲ್ಲಿರೋ MMF ನ N2I2 ಅಂತ ತಗೊಳ್ತೀರಾ, ಪ್ರೈಮರಿ ವೈಂಡಿಂಗ್ ಅಲ್ಲಿರೋ MMF ನ N1 into I1 ಅಂತ ತಗೋಬೇಕಾಗುತ್ತೆ. N1I1 ತಗೊಂಡ್ರೆ MMF ಬ್ಯಾಲೆನ್ಸ್ ಆಗಲ್ಲ. ಅಡಿಷನಲ್ ಫೋರ್ಸ್ ಕರೆಂಟ್ ಕೊಟ್ಟಾಗ ಏನ್ ಮಾಡ್ತಾರೆ, ದಟ್ ಇಸ್ I2 ಡ್ಯಾಶ್ ಕೊಟ್ಟಾಗ ನ್ಯೂಟ್ರಲೈಸ್ ಆಗುತ್ತೆ ಮೇನ್ ಫ್ಲಕ್ಸ್. ಅದಕ್ಕೆ N1I2 ಡ್ಯಾಶ್ is a MMF that will be produced in a primary winding that will be same as MMF produced in a secondary winding, that is N2I2. ಸೊ ಅದಕ್ಕೆ N2I2 equals to N1I2 ಡ್ಯಾಶ್ ಅಂತ ಬರ್ಕೊಳ್ತೀರಾ. ಸೊ ವಿತ್ ಹೆಲ್ಪ್ ಆಫ್ ದಿಸ್ ಯು ಆರ್ ಫೈಂಡಿಂಗ್ ದ ವ್ಯಾಲ್ಯೂ ಆಫ್ ಅಡಿಷನಲ್ ಕರೆಂಟ್, ದಟ್ ಇಸ್ ಟ್ರಾನ್ಸ್ಫಾರ್ಮೇಶನ್ ರೇಷಿಯೋ ಟೈಮ್ಸ್ ಆಫ್ current produced in a secondary winding. This is a theory about practical transformer on load. ಸೊ ಅದೇ ತರ ಇವಾಗ ನೀವು ಫೇಸರ್ ಡಯಾಗ್ರಾಮ್ ತಗೊಳ್ತಾ ಇದ್ರಿ. ಸೊ ದ ಫೇಸರ್ ಡಯಾಗ್ರಾಮ್ ವಿಚ್ ಇಸ್ ಡಿಪೆಂಡಿಂಗ್ ಆನ್ ದ ಲೋಡ್. ಹೇಗೆ, ಇಫ್ ದ ಲೋಡ್ ಈಸ್ ರೆಸಿಸ್ಟಿವ್ ಲೋಡ್, or else if the load is inductive load, or else if the load is capacity load. Three phasor diagrams are there. So if the load is resistive load, before that you should know the phasor diagram as I explained, transformer on no load. Phi is a reference. So this phi is produced due to Im. Im is in phase with the phi, and V1 leads phi at an angle of 90 degree. Before that, E1 lags phi at an angle of 90 degree. E2 and E1 are in phase with each other. Okay. Since the load is resistive load, therefore I2 is in phase with the E2. If the load is inductive load, I2 lags, you can observe here, I2 lags E2 at an angle of phi2. If the load is capacitive load, I2 leads phi2 at an angle of 0, whereas the direction of rotation is anticlockwise. So now, with the help of this Im and Ic, you will get I0 here. Okay. Then E1, sorry, to get the value of this I1. So before this, what happened? The total primary current which is having two components now. One is a no load current. Another one is the current which will be produced when the transformer is on load, that is I2 dash. If we add I0 and I2 dash, you will get the value of I1. Whereas I0 is having two components. One is Ic, another one is Im. Okay, so this is what you need to remember. So now let us go for the phasor diagram. So for this phasor diagram, you just observe. I'll explain how it is. So the flux is a reference, phi is a reference. To produce this phi, Im is in phase with the phi, and Im and Ic are quadrature in nature, that is 90 degree each other. If you add this Ic and Im, we'll get the value of Im. Then V1, which is in phase with Ic, or else Ic is in phase with a V1. Okay. So the angle between V1 and I0 is phi naught, and E1, E2 are in phase, which lags phi at an angle of 90 degree. I2 is in phase with E2, whereas the load is resistive load. So to get the value of I2 dash, the additional current is nothing but it is always antiphase to secondary current. I2 dash is antiphase to I2, that is secondary current. So if you want to get I2 dash, the antiphase of I2 is I2 dash. Then if you add this I2 dash and I0, you'll get the value of I1. A simple phasor diagram. Okay. If you want to understand in a Kannada means, so ivaga three loads, the transformer, it is the phasor diagrams are depending on three different loads. One the resistive load, ಇನ್ನೊಂದು inductive load, ಇನ್ನೊಂದು capacitive load. ಫಸ್ಟ್ ಫೇಸರ್ ಡಯಾಗ್ರಾಮ್ ಬಂದು ರೆಸಿಸ್ಟಿವ್ ಲೋಡ್ಗೆ. ಹೇಗೆ ಹೇಳ್ತೀರಾ? I2 is depending on I2 and V2 relation, V2 or E2. Okay. So ಇವಾಗ V2 and I2 in phase with each other ಇದ್ರೆ resistive load, I2 lags V2 ಇದ್ರೆ inductive load, I2 leads V2 ಇದ್ರೆ capacitive load. So like that you can see the first step is phi is reference, phi reference. So ಈ phi produce ಆಗಕ್ಕೆ ಏನ್ ರೀಸನ್? IM is in phase with a phi. IM and IC ಏನಿರುತ್ತೆ? 90 ಡಿಗ್ರಿ ಇರುತ್ತೆ. ಈ IC V1 ಗೆ in phase ಇರುತ್ತೆ. V1 which leads phi at an angle of 90 degree. If you add IC and IC ಮತ್ತೆ IM ಎರಡು ಆಡ್ ಮಾಡಿದ್ರೆ I0 ಸಿಗುತ್ತೆ. I0 ಮತ್ತೆ V1 ಅಲ್ಲಿರೋ angles phi naught. I hope you are getting. At the same time, the EMFs E1 ಮತ್ತು E2 which are in phase with each other and which lags phi at an angle of 90 degree. I2 is in phase with the E2 whereas the load is resistive load. I2 is in phase with the E2. So to get the value of I2 dash is always antiphase of I2. I2 dash is antiphase of I2. Andre opposite direction of I2. So I2 is there, you'll get antiphase of I2 is I2 dash. If you add I0 and I2 dash, you can get I1. Draw a line which is parallel to I0 from the tip of I2 dash. Then draw a line which is parallel to I2 dash from the tip of I0. Somewhere it will intersect. That is your I1. Similarly, for inductive load, phi is a reference. IM is in phase with the phi. IM and IC are 90 degree each other. If you add these two, you'll get the value of I0. V1 leads phi at an angle of 90 degree and IC is in phase with the V1. So E1, E2 are in phase with each other and this lags phi at an angle of 90 degree. Now the load is inductive load, so that I2 lags E2 at an angle of 2 degree. If you want to get I2 dash, antiphase of I2 is I2 dash. Hence, if you add I0 and I2 dash, you'll get the value of I1. So I1 is primary current, which is having no load current, which is having two components. One is no load current component plus full load current. Whereas I0 is having two components. One is IC, other one is IM. Similarly, see for capacitive load, phi is a reference. IM is in phase with the phi. IC and IM are quadrature in nature. And V1 leads phi at an angle of 90 degree. IC is in phase with V1. And the angle between V1 and I0 is phi naught. Similarly, E1, E2 are in phase with each other and lags phi at an angle of 90 degree. So now I2 leads E2 at an angle of phi 2 to get the I2 dash. Antiphase of I2 is I2 dash. Then by adding this I2 dash and I0, you'll get the value of I1. The angle between V1 and I1 is phi 1 for the all three cases. So these are the practical transformer on load. Okay. So we'll be having one more concept called phasor diagrams for transformer on load. So I'll explain that in a next video. Before that, you have to know about this concept. So if you're having any doubts regarding this particular concept, feel free to write in a comment box. If you really like this video, kindly do subscribe and share maximum to your friends. Thank you so much. Have a nice day.